Let's look through some more practice with these sampling distributions of proportions. So here we have a packet of seeds with this germination rate of 92%, and we're saying there's about 160 seeds in each packet. So first what we want to do is, if we're going to try to find probabilities of certain germination rates coming through, we need to know if we can pass the conditions. So whenever we're asked for the conditions here, we're looking for, do we have independence, randomization, and we want to pass that success failure condition. So for independence, it would be something like that each seed behaves independently of the others, something like that. What we'll do is just go ahead and assume we're good here. Randomization, they don't say it's a random sample, but we'll assume that when you put together 160 seeds, it's from a random bunch of 160 seeds. So we'll say those are both okay based on our assumptions. Success failure, we can actually prove. We would take 160 times 0.92 and then 160 times 0.08. And we would just need to calculate those values, which will give us, let's see, about 147 here and about 13 here. And for checking the success failure condition, you can go ahead and round to whole numbers. These values aren't being used for later calculations, so we just need to make sure they're larger than or equal to 10, which they both are, so we can move ahead. Since we pass all three conditions, that tells us that when we make our graph, we're going to have a nice bell-shaped curve. Defining the sampling distribution, what we're going to need is our mean for our sample proportions and our standard deviation for our sample proportions. So what's given to us, that 92% is our population proportion. It's what we expect to come through. And we have our sample size of 160. So for the mean, you just copy down that population proportion. For standard deviation, we're going to take the square root, take that 0.92 times 0.08 over our sample size of 160. And that's going to give us a standard deviation of 0.0214. So our distribution for our variable, it's normal since we passed those three conditions, centered at 0.92, standard deviation 0.0214. So sketch and label a model. There we'll be taking a bell-shaped curve. We'll be at 0.92 in the middle there. And then let's go 2 standard deviations above, 2 standard deviations below. So if we take 0.92 plus the 0.0214, we can expect a 0.9414. If we add 0.0214 again, 0.9628. And then if we take away our standard deviation, we'll see a number line of 0.8986, and take away another standard deviation, 0.8772. So this gives us an idea of, if we have a packet of 160 random seeds, what proportions do we expect to germinate? 92% we expect the most, but 96% would be likely, 88% would be likely, so we get an idea of what we can expect to come through. So what is the probability that more than 95% of the seeds will germinate? So we want this probability of being more than or equal to 0.95. So with that, it's like we want to go to 0.95 here and find the area to the right. So with that, we can go to GeoGebra, we'll set up our curve and find this probability. So we'll have a 0.92 for our mean, and a 0.0214, and then we want to find the area above 0.95, which is 0.0805. So there is an 8.05% chance, so that's our probability, that more than 95% of the 160 seeds will germinate. Right. Would it be unusual for only 140 or fewer of the 160 seeds to germinate? And explain. So that wording, unusual. We talked about it briefly when we looked at the empirical rule, and where it comes through is at 2 standard deviations away. If we're 2 standard deviations below or 2 standard deviations above, anything that lands out in those tails is considered unusual. And what we could use is the fact that in those tails was a 0.025, because that all came from our 95% rule. 95% in the middle, and then basically 5% split across those 2 tails there. So what we're going to need to do is basically see if we're landing in this lower tail here. So we're going to land somewhere over here. We need to figure out, are we landing in this region, where basically we'd have a smaller percentage than 0.025, or are we landing out here somewhere? So let's first of all, given 140, let's change it to a sample proportion. So that would be the same thing as 140 out of 160. So with that, our proportion would be 0.875. So what we want to do is go to our number line up here, and we can already answer it, because 0.8772 is 2 standard deviations below, and 0.875 is going to be over there. So really at this point, since we know 0.8772 is 2 standard deviations below and 0.875 is smaller, based on the graph, then this is unusual, because it's more than 2 standard deviations away. You can also prove this with a z-score. You take basically your sample proportion minus what's expected over our standard deviation. So for us, we'd be taking our 0.875, take away the 0.92, and then divide by our standard deviation of 0.0214. And if we plug this into the calculator, we should get something that shows that we're more than 2 standard deviations away from the mean, which happens with this negative 2.1028. So it's unusual since it's more than 2 standard deviations away from the mean. You can prove this a few ways. If you have your graph, you can show that it's less than that value that's 2 standard deviations away. You could use area. If you know you expect that 0.025, you can use z-score. So there's a few ways to show that it's more than 2 standard deviations away.